and we're here for broken Linux performance tools. Previously at Scale, I covered working Linux performance tools, and I also drew this diagram to show how where the tools provide observability, which is quite popular. This is a complementary talk. This is about broken Linux performance tools, particularly observability and benchmarking. My objectives are to bust assumptions about tools and metrics. The prior talk about working performance tools, it's the sort of talk that's fun to put together, as I get to talk about things that are exciting and things that work. But when you start to do a lot about performance analysis, you realize that's not what the landscape looks like. Some of the tools are exciting and work well. Many of the tools don't work well. And understanding what's good and what's bad is important for developing performance expertise. And so that's what this talk will help you accomplish. I will embrace the bad and talk about it, and we can see the sort of solutions that help us navigate through the minefield that is performance. So you'll learn how to verify and find missing metrics and to avoid the common mistakes of benchmarking. I'm going to discuss current software, and as I talk about various bugs, you might think, well, I can fix that. Yes, please do. So if in a couple of years I give this talk, it might be a shorter talk, and maybe we'll get it down to a 30-minute talk. That'd be great. So I work at Netflix, and we've just launched worldwide, so I have this great map of where Netflix is available. And that's right, it's almost everywhere. We're doing great. And we have Linux on the cloud, on AWS, tens of thousands of instances, and we have FreeBSD running our CDN. It's also an awesome place to work, and you might have seen the earlier talk from sysadmin to SRE, because we're hiring SREs, and there's many of us here today you can talk to about that. Please do. So the first section I'd like to talk about is observability. And I'll start with load averages. So something straightforward that we all should be familiar with. Load averages still get used at Netflix. It's one of the signals we use for auto-scaling groups. So whether to scale up a cluster based on load. The problem with load averages, well, there's two problems with load averages. One of them is the word load, and the other is the word average. Load on many other operating systems means CPU demand, but on Linux, load means CPU plus uninterruptible disk I/O, which can be a bit confusing. So you have that NFS server with a load average of 1,000 because you have all these threads doing uninterruptible I/O. So it's a bit tricky to understand. The word average as well, that's actually an exponentially damped moving sum. When you see the three numbers, 1, 5, and 15-minute load averages, it's not really the average for 1 minute. And to explain that a bit better, I took a workload which was a single hot thread, and I plotted the 1, 5, and 15-minute load averages over time. You can see the 1-minute load average eventually settles to 1.0. That's what it should be. The load average is reflective of how many threads were in the runnable state. But that's the 1-minute load average. At the 1-minute mark of having begun this load, the 1-minute load average is only 0.62. That's because it's an exponentially damped moving sum, and it's reflective of prior history. So what does 1, 5, and 15-minute actually mean? Well, they're the constants used in this damping equation. Or another way to put it, don't spend longer than 1 minute trying to understand this. It's just like a heartbeat signal to see if a server is healthy or a little bit busier. Yes. So you said that it was an infinite impulse response filter. Yeah. That's right. Now he said, thank you, it's an infinite feedback response filter, infinite impulse response filter. Right, and it's feeding back like the original signal. That's why it's actually useful to plot things, because when you plot things, you recognize patterns that aren't so obvious from numbers. And so quite often, if I'm trying to understand a workload or a metric which is related to this talk, you just plot it, and then based on the the profile, like you've identified yourself. It's like I've seen that before, and I understand that now. There's a whole science in performance engineering about modeling workloads and coming up with equations for them. I often find if you just plot them, you'll recognize the signals before you get that far. Top, percent CPU, the next metric I'd like to talk about. Well, this seems fairly straightforward. If I run top on a Linux system and it's telling me Java is eating 935% CPU in total, this is from one of our production instances, then that's fine. I know who's consuming CPU, it's Java. Of course, this is an instance with many CPUs, and so it can get that high. So this shouldn't be misleading or broken. Well, it can be, and I've heard of this as being posed as an interview question. Short-lived processes can be missing from top. So if you've ever done like a software build and you run top, all those short GCC processes and make and bourne shell, they disappear. So you don't see them in top's output. So you can use things like atop, which does event-based statistics and perf to get around that. One thing I particularly don't like is that short-lived processes vanish off screen updates. And so you see something and you go, wow, that's the thing that's causing the problem, and then the screen's gone. So I like to run pitstat instead, as it doesn't clear the screen, but it keeps printing an updated interval, and I can scroll back. But that's not so bad. Okay, so we're missing percent CPU in those situations. Misinterpreting percent CPU. And I want to dwell on percent CPU because it's one of the most common metrics we use to understand server behavior. So percent CPU can mean different things on different servers. So I had an example of 935% CPU. That's obviously not out of 100, so it's summing across multiple CPUs. So it can sum the CPUs, it can be a percentage of total CPU capacity, or it can do the same things historically damped, like using the exponentially damped function. It depends on the operating system, and so look at the man page. On Linux it is summing it up so that we can see the total consumed. Another problem. When I was creating these slides, I was looking for screenshots to put in there, and this is particularly interesting. The top of top has the system summary, and I can see percent CPU broken down into user, system, nice, idle, and so on. And then I've got the per CPU percentages. What often happens is you add up the per CPU percentages, and they don't quite add up to the summary line because you missed some short-lived processes. Okay, I already know that. In this case, the per process percentages added up to be more than the system summary. So we're seeing more here than we are up there. That doesn't sound right. Hands up if you think the system-wide summary is correct. Okay, so I've got like 4 people. Hands up if you think the per process summary is correct. Okay, so I've got like 3 people. Other people are unsure. You can see what's happening next. This sounds like a pretty good interview question. Actually, it's just trivia. It's a horrible interview question. Go read the source code and tell me which one is right. I've got the quote there. A man with 1 watch knows the time. With 2, he's never sure. Unless you're Mark Shuttleworth and you have that GPS clock in his house. So from CPU load.txt in the Linux source code, it says procstat, which is what's giving us that summary. Sometimes it cannot be trusted at all. And that's in the kernel source code. It's like, well, that's interesting. Good thing we don't use it for anything. No, actually, we use this for everything. All the performance monitoring products read procstat and get the information from there. Fortunately, it's not that broken, but it can be sometimes a little bit misleading or just flat out wrong. Both of those values can't be right. It does get worse. So that's looking at what top is giving us as percent CPU, and then looking at what the kernel is exposing as percent CPU. But looking at percent CPU as a metric itself, what is it anyway? A nice way to describe it is there is good percent CPU and bad percent CPU. So good percent CPU is we're retiring instructions. We're making forward progress on our program. unless they're spin lock instructions, in which case that's bad CPU because you're just wasting instructions. But generally, if I'm retiring instructions, I'm making forward progress. Bad percent CPU is where the CPU is busy, but the CPU cycles are not actually doing work. They are stalled, waiting on memory I/O, waiting on resource I/O, or thermal throttles, or some other event. We can understand the difference between good CPU and bad CPU by lots of different ways. So performance monitoring counters inside processors will tell us if you're stalled on cache misses, or main memory I/O, or LLC, or hardware resources. But a much simpler metric, similar to load averages in terms of simplicity, is instructions per cycle. This is similar to miles per gallon, but for CPUs. So, or in this case, it's more like gallons per mile. So it's that way around, miles per gallon. So a high IPC is where we are, for each CPU cycle, we are able to retire many instructions. And CPUs can do this because they execute instructions in parallel and out of order. They turn them into micro operations. A low IPC, and so to give you some numbers, a high IPC might be 2.0. A low IPC might be 0.5. And that is, on average, for every cycle, we only make forward progress on half an instruction. So IPC, it's like a miles per gallon metric. It helps us understand whether we've got the good percent CPU or bad percent CPU. And that's really important, because if I'm trying to make deductions based on percent CPU, like we should buy faster CPUs because we know we're CPU bound, well, it may make no difference, because if you're memory I/O bound, faster CPUs just mean you stall faster, but you're not making forward progress faster. So percent CPU alone is ambiguous, and it's actually a problem, a widespread problem, not just in Linux, but in all operating system tops, is they don't split percent CPU into retiring versus stalled, which is what they should do. Although it does get worse. So to describe this with a story, because things get even stranger, and like this surprised me. I was doing performance analysis of RxNetty versus Tomcat, and one of the metrics I like to use to quantify performance is CPU cycles per operation to understand these frameworks. And I found that the CPU cycles per operation for Tomcat was fairly high as I ramped up the load. When I began, when the CPUs were only 10, 20% busy. As I ramped up the percent CPU to 80% CPU, 90% CPU, just by throwing more load at it, the CPU cycles per operation went down. So the processor became more efficient at executing operations the more load you threw at it. Anyone tell me why? Like, it commonly happens. What's that? It's speed step. So speed step is one solution. What else is there? So like things get faster as you throw more load at it. Filling up threads. Caches. So like CPU hardware caches. So the more load you're throwing at it, the more you're lighting up the caches. You may just cache better. And yes. JIT could be doing it. Yeah, you could actually. You're fundamentally executing different code. And so at 20% CPU utilization versus 80% or much higher load, the instructions that get executed are different because JIT chose to do something different. And so it's apples and oranges, you can't compare the two. CPU could clock faster, Intel Turbo Boost. There's actually lots of reasons for this. And so I went through them and I checked the hardware caches, and it wasn't hardware caches. It was basically the same. It explained a tiny bit. And the number is, it was 1.8 times more efficient at high load than at low load. So I was trying to explain a 1.8x. It wasn't hardware caches. It wasn't turbo boost. I did a flame graph just to see if the functions or the overall code changed from low to high utilization, and that was the same. Yes? Was it real or perceived? Well, that's a good question, because I'm trusting various metrics, and so what do I even, how do I even know that I'm measuring percent CPU correctly? Right. Right, so I did know the actual delivered throughput of the system, but when you're trying to understand it in terms of CPU metrics like percent CPU, I would use other ways to double check that that was accurate, which is an important lesson of this talk. You have one more idea, yes? Right, like, yeah, as you drive load up, like the schedule and the networking stack can all behave differently. And so it can just be different code, and the flame graph will identify, wow, people are really thinking about this, this is great. Branch prediction. Branch prediction in the pipeline, because you're just loading it up, can be different, which should change. You should ultimately change IPC because you're taking the wrong branch and you're having to, depending on how that's calculated. So it's another possibility. So lots of possibilities. I went through a whole heap of them and it wasn't it. And I'll have to move on. It was the speed step, which was the first answer, so thanks. Speed step really broke my mind in this case in that at low load, at 20% CPU, the kernel, speed step is driven by the kernel, it decided to run the CPUs at 1600 megahertz, and when I ramped up to high load, the kernel said, you know what, I should just run the CPUs faster. The CPUs are now going at 3000 megahertz, and I'm trying to compare cycles per instruction based on my percent CPU utilization, and I'm comparing apples and oranges. It's not the same thing. This is a hardware box I'd set up, and I'd forgotten to set the Linux governor to performance, which fixes you at the 3000 or whatever. So what does this mean? It means if I tell you percent CPU, as a lot of people have helped out, percent CPU itself can be ambiguous because you need to know a lot of things. What is the IPs, the instructions per cycle? What's the actual clock rate you were doing? Because it could be speed step or turbo boost doing it differently in order to be able to comprehend that. How did I figure this out? It was a process of elimination. And so IPC should have covered many of the bases. It should have covered cache misses, branch prediction, if it's measured right. And IPC was fairly static across the range. And so that got me thinking about the actual cycles executed. So I started using those counters and could pretty quickly figured out that we were completely running at different clocks. Also used CPU flame graphs to see that the code was the same. And we weren't doing like polling versus interrupts and things like that. So percent CPU itself can be a complicated metric, and it can still be complicated because it doesn't account for whether cycles are stalled or retiring when you get down to the micro-operation level. And so at the micro-operation level, we have lots of different functional units in a processor, and they can execute things in parallel. And it's just a simplification to say the CPU was on or off from one moment to the next, when internally you have some functional units are on and some are off, and it may have more internal headroom for more processing. So it actually turns out to be a really complicated metric. Another metric we like to use in Linux that turns out to be fairly complicated is I/O weight. And I/O weight suggests the system is disk-bound, but it is often misleading. So, and the problem is, if I have higher I/O weight, let's say I'm comparing an option, so I'm trying a new configuration for my database, and I/O weight goes up. I may say that's bad because I've got more blocking, and I shouldn't do that configuration change. If I have lower I/O weight, that might actually be bad too. Since I/O weight, and to really try and understand, I've drawn a Venn diagram, I/O weight is an idle state. So if I'm idle, but I have pending disk I/O, then we call it I/O weight. But I could have pending disk I/O, but it's just covered up by CPU. So if you have an I/O weight problem on your system, just run steady at home and like burn up all those CPUs, and you've solved the I/O weight problem because you've overlapped it with CPU cycles. And so that's what actually makes interpreting this complicated. But so long as we do understand it at first. Understand it eventually. Free memory has been another confusing metric on Linux, and there's even a website, linux8myram.com, which has a picture of a penguin with a DRAM out of its mouth. It's a lot of these things are counterintuitive, and that's what makes things hard, is we need to learn them. When the free column goes down in tools like VMstat or you're using a monitoring tool, it may not be bad. It depends how it's calculated. And so most operating systems use the principle, if there is free memory available, use it for something useful. And so it's being used for the page cache or the file system cache. And that's why we use free minus m, and it gives us a clue there. So initially, I might have thought I had 2.6 gigabytes free. I've actually got 3.3 if I include the file system cache. Okay, so that sounds good. Now you run ZFS. ZFS hasn't hooked into this stuff yet. Free should be updated to handle ZFS. So now we get back to the problem where your free memory goes down to basically 0 on a system with ZFS. And the answer is, oh, don't worry about that. It's part of the ZFS ARC. You need to use ARCstat to figure that one out. So again, free memory can actually be complicated. You need to figure out how it's calculated. Yeah, it shows up as used instead of cached for ZFS. And it's in some ways you could call it a software bug in that free is trying to give us the notion of what's in the file system cache, and it hasn't been updated to handle ZFS. So, but again, it's important to understand the source of the metrics and how they're calculated. VMstat, classic Unix tool, also difficult to comprehend on Linux. The first line has some summary since boot values, but not all of them. In fact, I can't even remember which is which. I generally have to run a test workload to figure it out. Other Unixes, the first line is the summary since boot. So there is a difference on Linux. It's also used as a system-wide summary, which is pretty good, except we're missing networking. But that's okay. We can run netstat minus s, and then drown underneath all of the metrics it gives us. It's been getting better, so Linux has been adding more and more metrics like SYN retransmits, which I really like. But there is a lot of metrics to wade through. There can be over 200. One of the problems with this is it still doesn't include everything. And so I don't have really decent metrics to know, say, TCP queue utilization, how much is queued from one moment to the next. And there's other stuff that I want that's actually not part of netstat minus s, which you may assume is there when you see so many statistics. There are more minor things like typos and inconsistencies, and there's often no documentation outside of the kernel source code, and so it does require some expertise to comprehend. Disk metrics themselves, well, disk metrics are worse because all disk metrics are misleading. And you'll understand this if you've worked in the storage industry. Disk percent utilization or percent busy. Well, the problem is we often have logical devices that may be backed by multiple disks. And so a percent busy calculation just tells us that something was active during that window of time. We don't know if half the spindles were busy or flash drives or all of them. You don't really know the headroom, which is kind of the whole point of measuring percent busy or percent utilization. Disk IOPS can be misleading. If we're dwelling on that, we're using, say, IOStat, we're looking at it. Is high or low bad? It really depends on what you're trying to do. And disk latency. And so as people get better at understanding disk performance, they will start using benchmarking tools, looking at latency histograms of disks. But even then, it may not be what you think it is. There's been decades of work to make disk I/O asynchronous to the application. And so let's have write-back buffers, and let's have read caches at all sorts of different levels throughout the stack. And so in the real world, there's so much engineering work has gone into avoiding your application from ever going near the disks. And so dwelling too much on disk latency, you have to ask, why does it matter that much? File system latency matters more because you're going to talk to the file system. And so I find it much more useful to measure it there. File system, much more useful. That's what your application talks to. It has a big file system cache, but we don't have any file system cache hit or miss metrics in Linux. So this is just completely missing. We do need a hit-miss ratio. It's something I did hack up with ftrace, and another port's been hacked up with eBPF, so that at least we can get the ratio, the hit-miss ratio, out of the file system cache. So far I've covered some metrics many metrics that are misleading, some that are wrong, and some that are missing. And so just to pause and say what you can do about this, you need to verify and understand what the metrics are if they're important. Realistically, you don't have time to verify and understand the 50 or 60 metrics your monitoring tool may be giving you. And that's okay, so long as you're aware of which metrics have I verified and which haven't I. And so when you're using them to solve issues, you know, these 3 are known to be good because I spent half a day reading the Linux kernel source and testing them, and they work. All the other metrics, I don't know that they're good, but I can use them as clues. And so that's a mindset that's really helpful, knowing what is proven to have worked and knowing what you've yet to have the time to do to prove and verify. And so you can cross-check with other tools. Dynamic tracing is great for that. Test with known workloads. So you might have a benchmark tools can actually be useful for testing observability metrics. So I know this is my supposed throughput. What does the observability tool tell me? Reading the source, obviously, and using known to be good metrics. To find the missing metrics, that's even harder. And so use methodologies like the use method pose questions for metrics to answer. And that's a great way to discover that you're missing metrics. Also, if you draw a functional diagram of the environment or Linux or the application to try and figure out which parts you don't have observability for. Sometimes it gets a bit depressing and you think, can't we just burn it all down and start from scratch? And there's just been so much work in systems, metrics, and understanding and documenting that it's hard to do. Just as a wild speculation, there is one environment where they already have burnt all the metrics down, and they kind of do need to invent them from scratch, and that's some of the unikernels I've looked at. And so you can't log in and run vmstat and iostat and ps and top and get confused by all those metrics we've had for decades. And some of the engineers are already thinking about the problem of, if we have to reinvent it all, what should we do? So I'm not saying that will be the solution, but it's a surprising opportunity that maybe someone will figure out what metrics we should have, given a clean slate. Profilers. Linux Perf is a great profiler, and this can be used to do things like, this is another observability tool, but I'm trying to understand how the CPUs are being used by code paths. It has this nice hierarchy view, tree view. Unfortunately, it's very verbose, so 13,000 lines. And that's kind of a problem with today's profilers, is the output can be onerous to read through. That's the full output in one image. And this is why I came up with flame graphs, which uses a hierarchical visualization called an icicle plot, but this is upside down. And it shows the same data we saw in that the impossible slide of text, and I can much more easily navigate it. Great, sounds like profilers are a solved problem. We can just do flame graphs and everything works. Unfortunately, there are lots of issues with profilers. Yes, you had a question? If you just Google flame graphs or DuckDuckGo flame graphs, you'll find all the steps are online. Visibility. So when we tried to do this, we found you can use Java profilers, which Netflix runs a lot of Java, and they typically will show you the Java code, which I've colored green, but they can't see outside of the JVM. So I can't see kernel libraries. I have some visibility of GC. And there were various other problems with those profiles as well. Inaccurate or incomplete profiles. System profiles, like what Linux has with perf events, that's great because I can see kernel activity, but I'm missing stacks and symbols, so I can't see the Java methods. And this is one of those examples which I wanted to include in a broken performance tools talk where That's the real world. You'll often find the profilers don't work, and it requires some engineering time to fix this. We did this work at Netflix last year, and now JDK 8 Update 60 has the preserved frame pointer, so we can do proper system profiling. But don't assume profilers will work out of the box. It may be a few weeks of work to get them to see your code. The particular problem here was compiler optimizations, and it's how the kernel likes to walk stack traces, or profilers like to walk stack traces using the frame pointer register. And compilers have reused that as a general purpose register for years. So that's why GCC has -f no omit frame pointer, which you should always use because it helps debuggers and profilers. And how Netflix, we helped get preserved frame pointer put into Java for the same purpose. Missing symbols, just to mention it, if you're getting into profilers, you'll often find you can profile stack traces, but you don't have symbols. You just have these hexadecimal addresses. It's just another problem to work with. Linux does have some solutions, so perf events will look for these supplemental symbol files, and there's ways to create them for Java and Node.js. If you try and do instruction profiling, you find that instruction profiling has actually kind of been broken for many years. So here I wrote a assembly program that just does nops in a loop, and then I profiled it, and I found that somehow the CPU was jumping from one nop to the next. I could never, that's the percentages of samples, and I could never see the instructions in between. And there's various reasons why instruction profiling has been broken for many years. Skid, out-of-order execution, and sampling the resumption instruction. This is why more recently Intel has come up with things like PEB support, which Linux supports, so that you can get precise event-based sampling. So if you're going to go into profilers, some happy things of what you can do to address these problems. Do get stack trace profiling working. So get stack traces to work and symbols to work. It's worth it because you can then do things like create flame graphs. Also for observability tools, it's important to understand overhead. So TCP dump seems to be the genesis for many tools, and people do GUIs on top of TCP dump. I've solved lots of issues of TCP dump. It's great, but you do need to understand the overhead. And I'm always wary of anything that does per event-based dumping. Try TCP dump on a 10 or 100 gigabit Ethernet system, and you'll see dumping all of the packets, even just the headers, starts to incur high overhead. The screenshot I've got there was dropping packets, so it couldn't keep up. So there's various overhead costs of doing this. What I try and do instead is use, say, dynamic tracing and go into the kernel and do frequency counts of TCP events. If you have no other tool and you use TCP dump and you pay a price, but you ultimately solve the problem, that's okay. The most important thing about this is to understand there is a price to pay. strace is a much bigger price to pay. And an example here, a worst case example, DD of 1 byte from dev 0 to dev null is running 400 times slower if I run that through strace. What's interesting here is I'm stracing the accept syscall, which DD is not doing at all. It's not even doing the accept syscall, but it's that much slower. And that's because of the way it's doing instrumentation. It has to instrument all the syscalls before it can do the filter. And also the way strace currently works with ptrace is like putting metering lights on your application. It will set a breakpoint when you enter a syscall and when you exit, and context switches for every system call. So we should use more modern traces instead, like perf events. And they're much better, but there are some hidden dangers of things like perf events and system tap and ftrace. And just to come up with an example here, I've said, wow, perf events, I can record the scheduler switch event. It's pretty useful. Let's do all CPUs, call stacks, and it wrote a 100 megabyte perf.data file. So that's a lot of data. And this is only for 1 second. Imagine if I typed 100 seconds. Like I'd have a 10 gigabyte perf.data trace file. And my problem is I've traced something that's very frequent, so the scheduler switch event. When you use traces, and the same is true for all the traces, including, say, eBPF and dtrace, you have to be aware of the overhead of what you're doing. And so there's various costs. So if I'm dumping every event, that's high cost, like to a TCP dump file or perf.data file. If I'm doing in-kernel aggregations, it's much better. And then it's the frequencies of events. They need to develop some idea of how quick is the thing I'm trying to trace. Scheduler events are really quick, so I'm always careful if I go near the scheduler. But there are lower frequency events, like disk I/O is generally lower frequency, process creation and destruction. Of course, some tools make it pretty clear that they're going to slow the application down, like Valgrind has in its documentation. I will make your application run 20 to 30 times slower. So at least in this case, it does warn the end user. Java profilers can be even worse, depending on how they work, if you run these on Linux. Sometimes they have two modes, so sampling of stack traces, like at 100 Hertz, or tracing methods. And by now, you should identify tracing methods could be the really expensive one because of the frequency of events. I could do millions of methods a second. And they could slow the target. What I find weird is the documentation for these can describe method timing as highly accurate, even though your app runs 1,000 times slower. It's like, how can it be highly accurate? If my app is running 1,000 times slower, everything's going 1,000 times slower. Like race conditions could be different, like networking events are all different. So I did see a good talk about profilers or lying hobbitses that went into more detail. So for overhead, for profilers, you do need to understand how the profiler works. How is it instrumenting what it's telling us, and what's the frequency of events? Generally, if I'm going to do in-kernel summaries and it's less than 10,000 events a second, it should be negligible. If it's more than 100,000 events per second, you start to be able to measure it. Monitoring, I can mention quickly because a lot of the risks involved for Linux monitoring are the same that we saw for tools and metrics. So the tools can be quite misleading on the metrics they're telling you. They can be missing metrics, like our file system cache hit-miss ratio and some of the network statistics. So the problem that I see many monitoring tools do is they assume the system metrics are perfect. And the problem is, let's just plot them, let's just graph them. And of course, whenever I talk to vendors, that's not the problem. The problem is the metrics are broken and they're misleading and we're missing all these metrics. I don't need someone to graph this stuff. I need someone to fix this stuff. So that's kind of the problem we have. Another issue with monitoring is if it's built on some idea of event tracing, where we'll trace every event and then post-process, and that can incur a massive amount of overhead. And of course, doing this on the cloud-wide can make things all the more worse. So if your monitoring product is supposed to work on the Netflix Linux cloud of tens of thousands of instances, then how much data do you need to push around to monitoring servers to work? Statistics themselves can be quite misleading. And averages can be misleading because they hide latency outliers. Permanent averages can hide multi-second issues. So I had a customer with an issue in a prior job where their CPUs, I knew they had a CPU issue, but they were convinced they didn't because their monitoring system said they peaked at 80% CPU. 80% was the 1 minute average. And when we looked at the per second average, they were flatlining, and then there would be more idle and flatlining. So always understanding how the statistics are calculated or metrics. Percentages can be misleading as well. So if I hit my 99.9th latency, intuitively that sounds pretty rare. But if I'm processing millions of events a second like we are at Netflix, that happens all the time. And so we need to look more closely at those. What we like to do is to look at the distribution. And so there's lots of different ways to do that. This example, I've plotted the latency of disk I/O, latency on the x-axis, frequency of disk I/O events on the y-axis, and it's multimodal. So you have a low latency distribution of like half a millisecond, then a higher mode at 1.2 milliseconds. The average is in between them, which is just an interesting real-world example. It's when the average is supposed to be the index of central tendency. In this case, it's not. It bifurcates the modes. So that is quite misleading. If you're looking at averages, is you also want to look at the distribution so that you understand if you have a multimodal distribution or a long tail and the average is not what you think. Speaking of misleading things, visualizations can be misleading as well. And if you've seen my talks before, you know I'm not a big fan of traffic lights, people putting red and green colors in things. And so in Linux, we've got dstat and htop. And I like those tools. The tools are innovative in all sorts of different ways. Personally, not a big fan of the colors. If you like to use the colors and you find them useful, that's good. But for me, when I see things like my system time is 80%, that's green, that's good. And 20% user, that's red, that's bad. For me, I would color them around the other way. 80% system time, it kind of sounds like the Linux kernel is doing NUMA rebalancing, which we've seen, and like just burning CPU in the kernel. And here, top has got its own color highlighting for the same workload, which can be more misleading than useful. So I find traffic lights are good for objective metrics, like actual failures. They can be misleading for subjective metrics, where it can be latency or IOPS, and it's not clear. It's based on your business requirements what is good or bad. I'm not a big fan of tachometers either, and there's at least one Linux monitoring product that likes to use them, especially with arbitrary color highlighting or pie charts for real-time metrics. So what you can do for that section, for monitoring, it's the same as the observability tools. You need to be able to verify metrics and then understand overhead. For statistics, ask, how is this calculated? Is it an average over an interval? What's the calculation? And look at the full distribution. Just looking at it, you might see that you've got multiple modes or the shape of it. And for visualizations, you do want to use histograms and heat maps and flame graphs as they add value. The last section I've got is benchmarking. And benchmarking is extremely error-prone, to the point where I would say that almost 100% of benchmarks are wrong. And there's a nice quote I've taken from a paper called A 9-Year Study of File System and Storage Benchmarking. That sounds like hell. Who would do that for 9 years? Where they've said most popular benchmarks are flawed. You can see how restrained they are when they wrote that. And also, and this is what catches people, all alternates can be flawed as well. And so if people tell me, Brendan, I need to benchmark this, I'm going to use Bonnie++, whatever it is. And I say, no, don't use that. It's misleading, there's bugs, there's overhead, you'll shoot yourself in the foot. And they say, okay, what's the alternate? What should I use? And sometimes it's like, there's nothing. There's absolutely no benchmark that you will not hurt yourself with for this area. You're going to have to create yourself. And some people really struggle to get their head around this. It's like, but this is really popular. There's like 20 benchmark alternates on the internet. Can't one of them be true? It's like, no, actually none of them can be true. They can all be wrong. Like, you need to understand this. Some common mistakes. Testing the wrong target, very common. So you download some benchmarks, seems like a good idea, but you're testing something that doesn't matter for your actual workload. And so that's where I think I'm evaluating a storage product, and I think I'm testing the disks, but I'm hitting out of the file system cache. And so it's like, wow, my disks are doing like 10 gigabytes a second for one spindle. It's like, no, that's your file system cache. You're testing the wrong target. Choosing the wrong target. So at that point, you say, okay, I will do direct I/O, and I'll disable the file system cache. I will test the disks. Why? It's not actually real world, as I said earlier, because in the real world, you will have the file system cache. So you may as well test through the file system cache. You need to know what you're testing. Invalid results. Sometimes benchmarks do have bugs, just like observability tools and metrics. Ignoring errors. A great one I see is, and I've had this myself, where I get a great result out of a web server. I think, wow, look at this, I did 1 million events per second. I should publish. It's like, wait a minute. These are HTTP 500s, and like, they're all broken. Like, 100% of them are broken. And you discover that the error path is faster than the success path. So if you're wicked, you'd use that in your benchmarking results. Look how I broke 1 million events a second. It's like, yes, and they all failed. And it's because in the function, you do the error checking at the top and then like return error, and then you do the actual work. So it's no surprise the error path can actually be quicker. Ignoring variance or perturbations is another common error. And so the real world workload is not steady or consistent, which doesn't matter. And so we call it like sunny day performance testing versus rainy day performance testing. With sunny day testing, maximum throughput when it's a perfect workload. But in the real world, it's more like a rainy day where there's variation and there's perturbations, and you just don't have any insight into that because you never tested it. And of course, misleading results. If you're not paying too much attention, it's easy to benchmark A, actually measure something else, and conclude you've measured a third thing. Just to go through the types of benchmarks quickly, some micro benchmarks. These are the ones that test a specific function in isolation. And so file system maximum cached read operations per second, or network maximum throughput. These are pretty useful. They're useful because they're easy to debug. And so if you're trying to understand why a micro benchmark has regressed, there's not that much on the analysis table to get to the bottom of. There's lots of bad ones, like get PID in a tight loop or the speed of dev 0. And that's the problem, is it's easy to also test things that aren't very relevant. So you need to, or you're missing workloads that are relevant. So micro benchmarks, they're a useful tool, but you need to match it to the real world intended workload. And one way people do this is let's do macro benchmarks. That's where I will do my full client simulation of logging in and doing stuff and logging out. Common problems is misplaced trust, where you believe your macro benchmark must be realistic, but it's not. It's just like everything else. It can have lots of problems you need to debug. And they're also complex to debug. Now that you have everything on the operating table, you have to figure it all out. And so it's like, oh, so now you found a regression with a macro benchmark. I would try to reproduce using a micro benchmark just to make it quicker to analyze. Kitchen sink benchmarks are also popular. Let's run everything and then come up with like a value, like an average across them all. Lots of problems. The myth is that more benchmarks is greater accuracy, and it's more benchmarks is just more opportunities for errors. To mention a few in particular, Bonnie++ is a popular hard disk benchmark, or the website says it does a simple test of hard drive and file system performance. I had to do an analysis of this once, and I began with the first metric, which was the per character sequential output. And I found that what it was actually testing was it was doing 1 byte writes to libc via putc. libc would then buffer it. And by the time libc talked to the file system, it was doing 4 kilobyte writes. The file system and volume manager did its own buffering and placement, on disk placement and grouping. And by the time it talked to the disks, it was doing 128 kilobyte asynchronous writes. So I had a customer who was worried about this result, the per character sequential output, and thinking it's a disk result, and it's got so little to do with the actual disk. By the time you're talking to the disk, you're doing something totally different. And bizarrely found things like, oh, I can actually tune this, I can use set buffer, I can change the buffering inside libc. Has anyone ever tuned with set buffer in libc? Wow, someone has, excellent. So it was a learning experience. And of course, there could be other things. I could have ionize turned on, and so your benchmark is accidentally testing a Linux I/O throttle. So really error prone. You really have to get to the bottom of it. Bonnie++ did update their code. So this particular problem now does direct I/O. So we'll actually do 1 byte disk I/O. But just as an example of the sort of many issues you can run into. Another common one is Apache Bench. Single thread limited. So many times I see a result, but you're actually limited by Apache Bench being single threaded, which is why people use WRK. Another problem is there are some problems with AB's code, but there is another problem, and it's not so much AB's fault, but whether you use Keep Alive or not. And so I've had the situation where if I don't use Keep Alive, it becomes an unrealistic TCP stack benchmark because it's creating and destroying sessions for every request. And like your kernel system time goes through the roof. And it's like, okay, well, like, did you mean to test the TCP/IP stack? I think you're trying to test like a real-world workload. And if you use Keep Alive, then it can go at light speed because it keeps alive everything. And so now you become an unrealistic server throughput test. So again, it's misleading to begin with because you think it's going to give you a nice simple result, but you really have to dig in and think about it. to get value. And the last one I'll mention is Unix Bench. Unix Bench still exists. It's the original kitchen sink benchmark from 1984, published in Byte magazine. Lots and lots of, you'll run lots and lots of micro benchmarks that makes up the byte index. Things like pipe throughput and pipe-based context switching. Many problems, many problems. I've been meaning to write a blog series about all the Unix Bench problems in the hopes that I can stop people from using it. Unfortunately, I only got as far as the makefile. So it tells you run this shell script called run, and then it automatically creates a makefile for you. Okay, so I ran run, and this is what it does. This is all hashed out. Oh, look. For Solaris 2, let's use these options. I'm running this on Linux. I'm running this on like Ubuntu, and it's picking a Solaris 2 options. In the Computer History Museum last night, at Gaming Night, there was a copy of Solaris 8 sitting there. This is Solaris 2, and that's actually what Unix Bench is using as part of its makefile. So, but the problem is, it's like, okay, so it's picking the wrong thing. It should be picking the Linux thing, right? Let's uncomment this. And if you start looking at it, you might think, well, should it be minus 02 or minus 03 these days? Maybe I'll change that. No, don't change it. What are you doing? Like, if you change it, you're changing the benchmark result. And like you're baking in your choices into the numbers. You forget you did that. And you'll be telling your friends, look at my Unix Bench result, they're faster than yours. It's like, it must be the server. It's like, no, because you went and hacked at it, right? Because you thought, this is stupid. Like, why am I doing Solaris 2? I should go and uncomment this and go hack away. And so that's a really big problem. The Unix Bench documentation says, hey, the results depend on not only your hardware, but your operating system, libraries, and even compiler. So, and it says, if you want to publish any results, you should put your compiler versions with your results. So it's interesting in that the documentation told you all along, this is going to include the compiler and how you're doing it. Except it's rare that you see someone publish the compiler settings with the Unix Bench result. And people compile it up on different systems. It's really problematic to try and compare those numbers. I should finish the series of Unix Bench one day and like actually go through the micro benchmarks and why they're misleading. But I got a little bit depressed just at the makefile. It was innovating and useful at the time, but its time has passed. So what you can do about benchmarking, match the benchmark to your workload, and do this a methodology called active benchmarking, where you configure the benchmark to run in steady state, 24/7, and you do root cause analysis while the benchmark is running, and you answer the question, why is the benchmark result X and not 10 times X? Because if you can answer that question, you can answer the limiter, and then you discover the limiter is stupid because you configured it wrong or you're testing the wrong thing. And so you just go through the normal process of root cause analysis. This is great to learn performance, actually, because if you do root cause analysis on a production system, you don't really know what the limiter should be. At least with a known workload, a known benchmark, you have a starting point. In summary, observe everything. So how to get out of trouble. Trust nothing. Even though everyone is using that metric, it doesn't mean it's right. Metrics often can be misleading. Metrics can often be missing as well. And so you want to pose questions first and then find the metrics to satisfy them. And you might have to create new metrics. And so that's why I like my functional diagrams. Profile everything. So like Java mixed mode flame graphs. This will solve a lot of issues. It's really useful for benchmarking as well, to show what code is actually executing and what's on the table. Visualize everything. So I want to see histograms of latency. I want to see heat maps of latency, which is a histogram over time. So here's my bimodal disk I/O, and I can see there's a wide mode every 5 seconds or so. Great. That's what we want to see, more information. And finally, benchmark, nothing. Just stop doing benchmarking, and that problem will be solved. Or if you must do benchmarking, please do active benchmarking. So we analyze what's going on and get to the root cause. So I've got in my slide deck, I'll post it on SlideShare, I've got links and resources, especially things that aren't broken. Like I said, this is a complimentary for some scale talks where I talked about performance tools and things that work. And so if you leave this a little bit depressed, there are suggestions of things to do throughout these slides, and you can also check out my earlier talks about things that work. And that's my talk. Thank you very much. And we do have time for questions. I'll say before anyone runs away, there are some Netflix people here as well. If you'd like to talk to us about working at Netflix, it's an awesome place to work in 2016, so please hit up one of us. The questions? Yes. What's my favorite tool for NFS benchmarking? I used to do a lot of NFS benchmarking. You know, at one point at Sun, when I was doing it, I wrote a Perl program that NFS benchmarked because I was so sick and tired of the various proper tools being broken. And it got to the point where they said my Perl program was the gold standard of benchmarking. It's like, wow, you have to be kidding me. But it's a simple, the point was it was a simple program that used the interface. I actually published it and put it on, you can still probably find it on blogs.oracle.com. And the point was it was a very simple program. It used the, I just did syscalls directly. I should have written it in C. Like a nice simple C program that you can debug, you understand what it does. Because as soon as you start to use more complicated things, things get off the rails. If I had to do benchmarking now, file system benchmarking, because I just treat NFS as a file system, I do like FIO. FIO is nice. It gives you some distribution information on the output. It does assume a type of distribution, but it's not too bad. So if you're going to hit up a commonly used one these days, FIO is good. There's it's a minefield, lots of bad. Yes? Right. I mean, benchmarking is a pretty depressing area. And the question was, wasn't there times when compilers detected that they may be eventually benchmarked and like change the compiled output? And yes, there's stories like that. You have to debug everything and know what's going on. It's pretty crazy. Did you see a question? Yes. So what was so is the question? What's the relationship between processor queue length and CPU usage? So processor queue length, so run queue length on Linux is a nice measurement of saturation. So how many threads have been queued up waiting for their turn? Percent CPU utilization is how busy a CPU was during a given interval. Now you mentally may say, okay, my model is I'll go from 0 to 100% utilization. And then, if you keep throwing threads at the CPUs, I will then get queuing. And that sometimes happens, but sometimes it looks a bit different. So sometimes you'll get to, say, 50% utilization, and then you start to see queuing. And you think, what? How can I have queuing for CPUs when I have all this headroom? And so again, you debug it, and you find out that you're running Erlang, and it's p-bound to the CPUs, and they can't use the headroom because they can't un-p-bind themselves. Or you find out it's because of statistics and the sample interval. And so you may be sampling it for, it may be 1 second, during which 500 milliseconds, the CPUs are flat out, and you have lots of queuing, and for the remainder 500 milliseconds, the CPUs are idle. And so you end up with percent CPU utilization at 50%, but you had queuing. And it's like, how can this be? So always like get to the bottom of things, really useful, you'll learn what's going on. Yes? Okay. Yeah, the question is, have I seen it where the Linux perf events doesn't detect kernel symbols? No, but we are on Ubuntu, and things work pretty well. I do have some, like my own compiled kernels where if I mess up the compile, I can break perf and like the way it fetches symbols. It just sounds like if you, I don't think that's a perf problem. I could be wrong, but I just get to the bottom. If perf can't recognize kernel symbols. Yeah, if you're debugging perf and symbols, like run strace -fe open on perf and find out all the files it's opening and see if it's going to the wrong directories. You just have to go through some debugging. Yeah, I use ftrace to debug perf, and I use perf to debug ftrace, and right. Sounds like you just need to debug it, find out why the symbols aren't working. Next question. So the first question is, how do I measure IPC, and the Linux perf command does that. So you do need PMU access. I've got a PC under my desk for that stuff. And if you run perf stat command, it will give you the IPC summary. If you run perf stat -a sleep 10, it will do it for 10 seconds. If you go to my home page, I've got a lot of the perf examples. I've got a separate perf events website, and I've got all the perf examples for measuring IPC and cache misses and all that stuff. Perf's a really cool command on Linux, so it's a great go-to tool for performance monitoring counters. Next question was, have you used Sysdig? Yes, I contributed some chisels to Sysdig. I did a spectrograph for sub-second offset heat maps for Sysdig. Sysdig's pretty cool. It's nice to see innovation in the tracing space. One thing I don't like about Sysdig is that it is an event-based tracer, and so it passes all the events down to user level and then processes them. And I would rather see that summarization happen in kernel. However, they have done a pretty good job of making the overhead as low as possible. So it's not like my first instinct is like, oh, I can't see myself using Sysdig, the overhead will be too high. And then I tested it, and it's like, oh, it's actually done a pretty good job of lowering it. But yeah, it's pretty interesting. They are doing innovative stuff in Sysdig, so I'd love to see Sysdig pick up eBPF, the kernel engine, which will allow them to do some in-kernel summaries. Was the question, do I see differences between problems found on real hardware and virtualization? Yeah. When you're virtualized, there's just a whole heap of different issues. So like getting timestamps can be different because Zen's getting your timestamp. And like we've had issues where we've had to tune our clock and use a different clock source in Linux. And like I've never had to do that in hardware, but then it's something that's virtualized, it's a hypercall. And so, yeah, there are times where you need to know. Of course, you're using Paravert drivers that are coalescing I/O together. It is a different beast. But if you're really good at one, so let's say you come from a hardware background, you go to the cloud, you will pick it up because you've worked on similar issues before. But definitely, it's a different beast to work with. Yes? So the question was, what tools do I use to analyze memory? If it's just high-level memory statistics, then you do get a lot of the /proc counters, /proc meminfo. You've got PS. It should be fine. You do need to understand like the difference between shared memory and then dirty memory, whether the application has dirtied it so that it's actually page faulted and is allocated physical main memory. And so I use pmap -x a lot. pmap. So pmap -x and the process ID is really fast on Linux, not so fast on other operating systems. It's really fast and it'll dump the memory address space and you can see the different types of memory. So use that to get to the bottom of a lot of process memory issues. If it's kernel memory, things like slab info, and then other stuff out of proc. Yes? Yep. So comparing Linux to FreeBSD in terms of, say, observability tools, it's different. At some point, I'd like to do a differences talk because it'd be pretty interesting. So FreeBSD, there's a lot of common things. Like you've got your tops and your PSs and your VM stats and IO stats and whatnot. One thing I like about FreeBSD is PMC stat has a better by default grouping of performance monitoring counters. You've got dtrace on FreeBSD, which is really easy to use. You can walk through kernel. Like I've written lots and lots of dtrace scripts, so that's currently much more developed on FreeBSD than the equivalent right now on Linux. So right now in Linux, I'm using things like ftrace and perturbations and eBPF to do kernel-based tracing, things that are inbuilt into the kernel. So it's different, but FreeBSD is pretty good. And like right now, until things like eBPF and ftrace surpass, I generally, it depends on the performance issue I'm working on, but I can often have a better time on FreeBSD than I do on Linux, just because there's a lot of stuff there. So it's a nice thing to check out if you haven't checked out already. And of course, Netflix has lots of FreeBSD on our OCAs, which is our CDN. I'll take one more question and then we'll break, and you can ask me questions in the break. I saw one more question. Okay, thank you. Bye.